The year is 1939. Europe is holding its breath, and the thunder of piston engines, Merlins, Cyclones, and Griffins, is about to define the greatest air war in history. For those of us who lived through or followed that era closely, the sheer capability of a plane like the P-51 Mustang seemed like the pinnacle of speed and endurance. It was a mechanical marvel, the best that conventional aviation could offer. Many of us remember the fierce debate at the time. How much more speed could a propeller plane possibly achieve? The engineering consensus, held by the most brilliant minds in the Royal Air Force and the U.S. Army Air Corps, was that we'd hit a hard ceiling. This wasn't a failure of imagination. It was a matter of basic physics, specifically the propeller tip speed barrier. When a propeller blade spins so fast that its tips approach the speed of sound, the air resistance and turbulence suddenly become immense. You get less thrust and a massive amount of drag. It was the point of diminishing returns, and therefore everyone was stuck in the same engineering rut. For all the genius packed into those radial and V12 engines, their power delivery was fundamentally limited. The military establishment looked at the next step, true jet propulsion, and mocked it. To them, it wasn't an inevitable technological leap. It was a distraction. It was a boy's fantasy, a science fiction pipe dream that defied proven engineering. The engine needed to propel a plane at hundreds of miles per hour would be too heavy, burn too much fuel, and destroy itself within minutes from the heat. So they confidently dismissed the threat, believing that if war came, it would be fought on familiar, propeller-driven terms. It's easy now, looking back from the perspective of modern jet travel, to think the jet was always coming. But the truth is, the entire world of aviation was ready to bet against it. They believed their axis of power, the propeller, was unbeatable. This is where the story shifts to one man. While the highest military echelons and senior engineers were laughing, one young Royal Air Force flight cadet, a technical genius who couldn't afford university, was silently drawing the future. His name was Frank Whittle. Whittle knew the answer wasn't to turn the propeller faster, it was to remove the propeller entirely. In 1928, he wrote a thesis titled Future Developments in Aircraft Design, which laid out the principles of the turbojet engine. The British Air Ministry, the institution he desperately wanted to impress and serve, took his revolutionary idea and filed it under the category of impractical for a decade. This isn't just a footnote in history, it's the core problem that nearly delayed the jet age for a century. The solution existed, therefore the problem wasn't technical, it was institutional arrogance. Many viewers tell us that the most frustrating part of history is seeing brilliant ideas killed by bureaucracy. This is a classic example. Whittle's design was simple: a continuous flow of air through a centrifugal compressor, ignited in a combustion chamber, and exhausted out the back at high speed to create forward thrust. The physics of it were clean, powerful, and circumvented the propeller tip barrier completely. It offered the only pathway to speeds beyond 450 miles per hour. But Whittle lacked the credentials, the money, and the political pull. He needed state-level support, but the state was busy proving why his idea couldn't work. This left the world, and the future of the war, dangerously vulnerable, because elsewhere, others were beginning to think similar thoughts. And the one thing the Allied experts didn't consider was that their mockery was the Axis' greatest psychological defense. They weren't just building a faster plane, they were unknowingly building a secret weapon, a psychological hammer that would change the nature of air combat forever. The failure to recognize Whittle's genius wasn't a minor oversight, it was a systemic error that guaranteed years of trial and error setbacks. If you want more of this kind of deeper historical analysis, hit that subscribe button. It tells YouTube and us that this is a story worth remembering. The slow pace of official Britain would soon be contrasted with the brutal efficiency of its enemies, and therefore the world would soon pay the price for ignoring Whittle's blueprint. Whittle himself was the answer, yet he was dismissed. History suggests that this act of betrayal and dismissal is the fuel that powered the Axis-mocked jet dreams, making the ultimate victory that much harder. The year is 1928, and a young man named Frank Whittle, a mere flight cadet at the Royal Air Force College Cranwell, is sketching a revolution. He wasn't a titled aristocrat or a seasoned industry magnate. He was a working-class kid who excelled through sheer talent. He felt the limitations of the propeller deeply. It was a ceiling on speed, and therefore on the very future of aerial warfare. He saw clearly what the established experts missed. The problem wasn't the engine's power. It was the mechanism used to translate that power into flight. He proposed, in a thesis for his course, a radical concept: the continuous flow gas turbine. This was the theoretical birth of the jet engine. He wasn't the first to think about reaction power, but he was the first to design a practical engine that could achieve it. His idea, in essence, was the same simple four-step process still used today: suck, squeeze, bang, blow. Now this is where the story turns into a classic tale of the inventor versus the institution, and it's why the Axis mocked jet dreams. They knew their competition was slow to adopt radical change. Whittle submitted his formal design to the Air Ministry in 1930, hoping for support, funding, and recognition. But the response he received was a polite yet firm "no, sir." The chief scientist for the Air Ministry's Directorate of Scientific Research, William Hawthorne, reviewed the plans and gave a definitive verdict. He claimed the engine's design was entirely impractical. The reasons were complex, but essentially boiled down to the enormous weight of the necessary compressor, the excessive amount of fuel it would consume, and the inability of existing metallurgy to handle the sustained high temperatures in the combustion chamber. In their view, the design would destroy itself before it could lift a plane off the ground.
This rejection was the scroll-stop interjection of Whittle's early career. It was a stunning blow. The British establishment, fixated on incremental improvements to piston technology, literally filed Whittle's revolutionary patent application under the category of non-starter. Think about that for a moment. This young man had presented the blueprint for the next century of flight, therefore ensuring air superiority in the coming war, yet he was met with nothing but cynicism and bureaucratic coldness. It wasn't just a missed opportunity, it was a conscious decision to bet against genuine innovation. Because of the Air Ministry's dismissal, Whittle had to pursue his work on a Strushing. He let the patent lapse because he couldn't afford the renewal fees, a fact that would later cause him and Britain great grief. But a few former colleagues believed in him. In 1936, they scraped together enough capital to form Power Jets Ltd., establishing a small, privately funded company. The initial funding was a pittance compared to the massive government budgets poured into piston engine development, but it gave Whittle the bare metal and shop floor he desperately needed. This struggle is the true heart of the invention story. If you had the blueprint to win the war, but no one would fund the metal, would you give up? Many viewers tell us that the emotional reward of Whittle's perseverance is what keeps them invested in this history. The real challenge now became solving the technical issues that the Air Ministry predicted. They were right that the hurdles were immense. The materials of the day simply weren't designed to withstand the hellish internal temperatures the jet produced. Whittle and his small team spent years working in near secrecy, battling combustion instability that threatened to shake the entire rig apart, and struggling to find alloys that wouldn't melt in a critical moment. The best ideas require a commitment beyond the initial spark. It's the reps, the constant trial and error that prove the principle. Therefore, every successful bench test, every minute the engine ran without exploding, was a major triumph. The breakthrough came with the W-1 engine, Whittle's first production-ready prototype. On April 12, 1937, this small, shrieking dynamo ran successfully on the test bench. The sound it made was unlike anything heard before, a high-pitched, terrifying roar that signaled a new age. This single event was the purple payoff for years of personal financial risk and professional rejection. But even after this initial success, the Air Ministry remained skeptical and guarded, offering only grudging limited support. They wanted to maintain control and refused to give the project the full national priority it deserved. This bureaucratic friction became the central, debilitating obstacle to rapid development. Here's the terrible truth, the chilling German parallel. But even as the British were celebrating their small victories, the Axis was already flying. Hans von Ohain had his engine, a contemporary to Whittle's, airborne in the Henkel 178 nearly 2 years earlier. This was not a private venture. The German jet program, backed by the full, state-funded resources of the Third Reich, was advancing at a frightening pace. This comparison is a direct, sharp, contrasting word that should make us uneasy. The Axis mocked jet dreams publicly, yet secretly deployed their greatest engineering talent. Therefore, every slow, bureaucratic step taken by the Allies was a critical vulnerability now being exploited by the enemy. Our failure to support Whittle meant we were giving Germany a free pass. The Allied jet programs were plagued by this initial rejection and the resulting culture of slow-motion development. Detail the technical hurdles. The alloys were not up to the task. The kerosene fuel, delivered at high pressure, often led to combustion instability. These were problems that demanded years of trial and error, not months. The urgency of war had not yet fully penetrated the rigid scientific hierarchy. This begs a critical question for all of us who value persistence. When did the grinding effort of trial and error become a greater threat than a single failure? The constant need for secrecy meant that instead of benefiting from mass production and collaboration, early jet prototypes often cannibalized parts from failed experiments, making the first successful Gloster E-2839 jet flight as much a miracle of improvisation as engineering. Microstory: the Gloster E-2839 jet prototype. The first British jet engine, an act of genius, was now trapped by a slow, state-controlled process. This operational paralysis became the overwhelming problem that Britain could not solve alone. The UK's industrial capacity was already stretched thin, supplying the massive needs of the Bomber and Fighter Command. Therefore, by 1941, the British High Command faced the brutal realization. They had the blueprints, but they did not have the production capability to scale the jet engine quickly enough to impact the war. This led to the ultimate contrarian snapback. The British military, having once rejected Whittle and forced him to let his patent lapse, decided to hand the WWII engine and its entire set of plans to their greatest industrial ally, the United States. They didn't just share the technology, they gave it away, hoping America's famously ruthless industrial might would make up for Britain's slow start.
The British mission, led by Sir Henry Tizard, delivered Whittle's secrets to the U.S. Army Air Corps. The inventor who couldn't secure funding from his own countrymen would now see his invention realized by a new, more dynamic partner. The promise of America's industrial might was the only hope of accelerating the jet age and beating the Axis to full deployment. The transfer of technology was a moment of true humility and desperation. It was a conscious choice to sacrifice national pride for the possibility of victory. This act of giving away the core intellectual property is the final, undeniable snapback. The British rejected the inventor, but then handed the entire idea to a new partner. And that new partner was General Electric. This decision to draft off the credibility and power of American industry was not easy, but it was necessary. The race to the sound barrier was now an American race, and the success of America's first P-80s would depend on the sheer scale and speed of their manufacturing sector. This transatlantic exchange of blueprints was the moment the world's most powerful democracy finally got serious about the jet age. The transfer of Frank Whittle's technology across the Atlantic marks the critical shift from isolated genius to industrial reality. This is where the story connects deeply with the memory of American industrial power, a time when our capacity to produce dynamos, airplanes, automobiles was unmatched. The year is 1941, and the blueprints that were scorned by the Air Ministry are now in the hands of General Electric, GE, in Lynn, Massachusetts. This introduction of GE sets a new, faster tempo. The British had the brilliant concept, but the American team had the dynamo, the industrial capacity, the engineers, and the sheer volume of material needed to scale this revolutionary yet fragile machine. The blueprints were British, drawn in metric standards, utilizing English materials and relying on UK production methods. Therefore, the entire engine had to be completely re-engineered from the ground up to fit US imperial standards and manufacturing processes. This wasn't a simple translation, it was a total redesign under a brutal ticking clock. Think about the sheer scale of that challenge. They weren't just converting measurements, they were converting an entire philosophy of engineering mid-war. This required not established aviation veterans, but an audacious team of young electrical engineers and industrial designers at GE's Lynn facility who were willing to stake their careers on a machine that shrieked and threatened to shake itself apart. This team was responsible for building the future on faith, using the blueprint of a British man they'd never met. Many of us remember that kind of focused, high-stakes manufacturing pressure from the war years. It's what defined our industrial backbone. This emotional resonance is the micro-reward that draws you in. The American team at GE, led by engineers like Dale Stride, tackled the most immediate and daunting hurdle: metallurgy. The intense temperatures created by the gas turbine demanded alloys that simply didn't exist in mass production. The key was the centrifugal compressor, the squeeze part of the engine, which had to spin at breakneck speeds without failing. The British Whittle engine had pushed current metal technology to its limit, but the Americans had to create new limits entirely. This effort resulted in the first American jet engine, the General Electric IA. This engine and its direct successor, the I-16, proved that the jet could be mass-produced with consistency and reliability. This rapid scale-up in production capacity was the true victory of American industry. The engineers proved that the rejection faced by Whittle was not a rejection of the idea, but a rejection of Britain's ability to execute it at speed. The US delivered the capability that the UK could not. But even the successful I-16 engine was deemed too weak for a truly effective fighter jet. It was powerful, but it didn't deliver the necessary thrust for the decisive air superiority the military demanded. So the next iteration had to be a giant leap, a major redesign, the powerful I-40 engine. This demanded a massive, almost reckless risk. The Air Force had to fully commit to this new, untested technology, betting that the I-40 would deliver the speed needed to outmatch whatever jets the Germans might be secretly preparing. This shift from incremental progress to a bold, high-stakes commitment is what separates the Dynamo from the drawing board. If you've found yourself frustrated by small failures like Whittle, but believe in the power of a committed, focused team, please hit that like button. It tells YouTube this is a story worth remembering for the grit and determination it showcases. The Air Force now urgently needed an airframe specifically designed to house this monster I-40 engine. This need created the dramatic value loop that pulled in the next major player in the story. The power of the engine was demanding an equal, radical approach to the airframe, and therefore the project was now shifted to an aviation giant known for speed and secrecy. The engine was revolutionary, but the plane it flew in had to be a revolution in design, too. The story of the GE Dynamo is one of unsung heroism. Electrical engineers becoming jet pioneers, overcoming the legacy of a metric system and skeptical bureaucracy, and laying the metallic foundation for the American jet age. The success in Lynn, Massachusetts therefore set the stage for the final incredible push to get America's first jet fighter, the P-80 Shooting Star, into the air. The massive industrial effort at General Electric had solved the engine problem. The powerful I-40 jet engine was a reality. But now the military needed an airframe revolutionary enough to contain it. The power plant was ready, therefore the final stage of the jet age relied entirely on finding an aircraft designer capable of equal, ruthless speed.
This is where the story shifts to the West Coast and introduces a legend of American aviation, Clarence Kelly Johnson. Johnson was the head of Lockheed's Advanced Development Projects Division, a small, highly secretive, and deliberately unconventional group known informally as the Skunk Works. The name itself, drawn from a joke about the smell emanating from a nearby plastic factory, underscored their anti-bureaucratic philosophy. The Air Force knew that sending the I-40 requirements through the standard military contracting process would guarantee delays. The war was heating up, and intelligence suggested the Germans were accelerating their jet program. Therefore, the Air Force bypassed all conventional channels and handed the contract directly to Johnson with a single, audacious demand: a revolutionary airframe in record time.
Johnson's promise became known as the 150-day miracle. He committed to designing and building the prototype for the new jet fighter, the XP-80, from a clean sheet of paper to flight readiness in just 5 months. This incredible tempo was proving that American speed and ingenuity could not only build the engine, but wrap the airframe around it faster than any nation on Earth. The stakes weren't just a plane, they were global air superiority. The development was a contagious finale because the work pace at the Skunk Works was infectious. They didn't have meetings, they had conversations. They didn't have committees, they had committed engineers. Johnson gave his team near total autonomy, trusting their expertise and demanding only one thing in return: speed and results. The design choices required were as radical as the timeline. The I-40 engine was huge, and placing it mid-fuselage, as the British did, was too complex for rapid servicing. Therefore, Johnson designed the plane around 2 long ducts that sucked air from the wing roots and fed it directly into the engine, which was mounted in the rear fuselage. This allowed for a much cleaner nose and simplified maintenance. But that clean design created a new problem. The plane was designed for unprecedented speed. Therefore, the wings had to be exceptionally thin to reduce drag, but thin wings presented structural and fuel storage challenges. Johnson's team solved this by using innovative integral fuel tanks built directly into the wing structure and by pioneering the use of laminar flow wing sections to achieve sustained high speeds. This focused commitment, operating outside the standard bureaucracy, is the essence of American industrial strength. If you believe in the power of a small, trusted team to deliver big results, take a moment to hit that like button. It helps us keep these stories in the public eye. The pressure was relentless, and the final stages involved incredible improvisations. The XP-80, named Lulu Bell by the team, was completed in a mere 143 days, a week faster than Johnson's promised 150-day miracle. The engineers and mechanics essentially lived at the plant, driven by an unshakable belief in the destiny of their project. The ultimate payoff came with the first flight. After a nervous delay caused by a minor engine fire and a necessary modification, the XP-80 Shooting Star took to the air on January 8, 1944. The plane's performance was staggering. It reached speeds that were, at the time, impossible for any propeller-driven fighter. The quiet whine of the jet engine, compared to the thunder of a piston, signaled a profound and irreversible end to the old ways of aviation. The machine that Frank Whittle had once drawn up, the machine that had been mocked by the Air Ministry, was now, through the collective genius of the British concept and the American Dynamo, a fully realized weapon. However, here is the final, compelling historical irony. But despite the success and the tremendous effort, the P-80s were too late. They were ready for the final Axis push and were deployed to Europe for combat testing, but the war ended before they could truly see combat. The lack of combat service does not diminish its achievement. The P-80 therefore became the silent winner of the air war. Its existence, its sheer speed, and its successful deployment to Europe irrevocably changed the global balance of power. The Germans knew it, and the Soviets knew it, that the American jet age had arrived, and it was fast. The P-80 Shooting Star laid the direct foundation for every subsequent American jet fighter. The knowledge gained from its design, its engines, and its manufacturing process led directly to the famous F-86 Sabre, which would go on to prove American air superiority in the Korean War. The blueprint, once a secret, then a gift, was now the universal standard. If you want to dive deeper into the early jet age and see how the lessons learned from the P-80 directly led to the legendary F-86 Sabre, check the description for related videos. It's the perfect next step in this amazing history. The contagious finale of the P-80's development taught the world that the greatest innovation often requires a radical break from convention, fierce dedication, and the industrial might to scale an impossible dream. So that is the true, complicated story of the blueprint that went from a flight cadet's daydream to the foundation of American air power. We've seen the entire cycle: the initial disbelief and mockery, the isolated, grinding struggle in the workshops of Britain, the necessary transatlantic partnership driven by necessity, and the ultimate, definitive success achieved through American industrial speed. The story of the P-80 shooting star is not just about a machine. It's about a fundamental lesson in life and innovation. The greatest, most disruptive changes often come from the people and the ideas that are most aggressively dismissed by the established way of thinking. They may tell you your idea is impossible, too expensive, or just plain wrong. But if the underlying physics and the dedication are sound, persistence will eventually find its reward. The jet age arrived not because the establishment finally said yes, but because Frank Whittle refused to hear no, and because a handful of ambitious American engineers refused to be bound by convention. This whole journey, the engine, the airframe, the politics, is a testament to the power of a committed vision. Don't feel overwhelmed by the detail, just absorb the flow of the story. The key to innovation is to recognize the wall that everyone else accepts as firm and to find a way, like Whittle, to go right through it. If you enjoyed this historical dive and want more like it, hit that subscribe button. It helps us know which pieces of history matter most